All right, let's do this example of the binary star example. So we're going to use the combined mass equation. So here's of course what it says: the two stars which are separated by a distance of 15 astronomical units and a period of 10 years, find the combined mass of the binary system. All right, here, let me get my. All right, this is the equation that we're going to use. We have the combined mass, which is little m. Oh, hold on just a second, I got the eraser on. We got little m plus big M. And you know, it's just two different masses, right? You could call them M1 and M2, that's perfectly fine. So I always put parentheses around it to indicate that that's the combined mass is equal to, is equal to a cubed divided by p squared, where a has to be in astronomical units. So remember, they gave us that it was 15 AU, and that p, I'll do it over here, p is, the period is 10 years. All right, so everything's already in the proper units, so all we have to do here is put the numbers in and do the calculation. So it's going to be 15 raised to the third divided by 10 squared. All right, and I've already done this in my calculator, and so you should do it too. And so here's what the answer comes out to be. So it's 33. That doesn't look very nice. Sorry, let me erase that. Sorry. 33. Eraser doesn't work very well. So sorry about this. I'll get better at this. All right. Anyhow, sorry. All right, go back to the pen. So it's going to be 33 point what is it? 75, and it's supposed to be a 5, and it's times the mass of the sun. Right, the numerical value turns out to be 33.75 times the mass of the sun. Right, and this combined mass, this, you know, little m plus big M, is always in solar units. All right, so try that yourself. That's the example. Here, so let me actually keep going here. So let's do the other one, which is the Doppler shift. Let me see if I can switch back to it. All right, so here's the other problem. It says the Lyman alpha lines, that doesn't, you know, that's a particular wavelength. That's all that's important about that. Is 121.6 nanometers. If that wavelength in a distant star is measured to be 121.9 nanometers, how fast is the star moving, and is it moving towards or away from us? So the thing is, like, if you know, the thing is to calculate delta lambda, right? So lambda is going to be the moving object. So in this case, it's the distant star. It's 121.9, and then the one in the lab, that's what we call lambda naught, is 121.6. All right, so here, let's write all that stuff down. Go back to Paint here, and let me switch this real quick. New, and don't save. Sorry, that's okay. So this is what we're going to calculate. All right, so it's this equation. The velocity of something using the Doppler effect is going to be delta lambda. I'll write it like that. So this thing, the delta lambda, that's actually the shift divided by lambda naught. Lambda naught. Sorry, that's supposed to be a little circle, and times the speed of light. Let me just, well, let me write all this out. Okay, so this is equal to, so lambda, right, which is the moving wavelength minus the wavelength in the laboratory divided by the wavelength in the laboratory, right? And then multiplied by the speed of light. Now, one thing I should mention, so this whole thing is multiplied by the speed of light, right? One thing I should mention is for this particular one, I mean, normally we use the speed of light as 3 times 10 to the 8th. But what we're going to do, and I'm going to write it over here, so this is just a separate thing. The speed of light here, we're going to represent in kilometers per second, right? So it's just much more common because that's the, stars are usually in hundreds of kilometers, traveling at hundreds of kilometers per second, all right? So we're going to use 3 times 10 to the 5th kilometers per second. That's kilometers per second. Sorry, it's supposed to be kilometers. All right. So let's do this problem completely now. So the velocity for using the Doppler shift, we're going to use this lambda minus lambda naught. So remember, lambda was the moving wavelength, so it's going to be 121.9 minus 121.6. Right, and then because that's the wavelength in the laboratory divided by the wavelength in the laboratory, 121.6. So that's a decimal point. All right, and then times the speed of light in kilometers per second. So it's going to be, this entire thing is going to be multiplied. So this is just a fraction, right? But notice another thing. I'm leaving it in nanometers because the numerator and the denominator are both already in nanometers, and the nanometers cancel, and so it's just going to be some fraction times the speed of light in kilometers per second, right? So it's going to be times 3 times 10 to the 5th kilometers per second. All right, so when we do this, what number did I get? So I get 740.1, 740, and this is 7, 0.1 kilometers per second. All right, so there's our answer, right? So that's our example using the Doppler shift. All right, so we get to the, let me stop this.